Good morning, everyone. Today we will continue with Chapter 5, Part 2, The Resurgence of Infectious Diseases. In this part, I will discuss the Ebola virus, West Nile virus, Zika virus, Influenza virus, SARS, tuberculosis, and others. Let's begin with Ebola. Ebola virus disease. Ebola represents the other end of the viral spectrum, fast, loud, and incredibly lethal. Let's look at why this virus causes such panic. The clinical presentation of Ebola. Ebola is a hemorrhagic fever. It causes the body's vascular system to leak, leading to severe internal and external bleeding, with mortality rate reaching 90%. It spread via direct contact with body fluids, often during caregiving or traditional funeral rites. The world saw the true potential of this virus during the 2014 outbreak. The 2014 West African epidemic. The 2014 epidemic was the largest in history, killing over 12,000 people. It highlighted the risk of zoonotic spillover, likely from fruit bats, and proved that in a globalized world, an outbreak in a remote village in Guinea can reach Dallas, Texas within days. This is the states in the United States of America. Despite the tragedy, this era produced significant scientific breakthroughs. The scientific breakthroughs in Ebola. We now have the RVSV-ZEPOV vaccine, which provides high level of protection, and new antibody treatment like REGNEP3. These tools have shifted Ebola from death sentence to a manageable disease, providing the infrastructure exists to deliver them. In the United States, the fear of Ebola sometimes outpaced the science, leading to ethical dilemmas. The Hickox fiasco, fear versus science. The case nurse Cassie Hickox demonstrated the tension between political fear and public health evidence. Mandatory quarantine of asymptomatic healthcare workers was found to be scientifically unnecessary and counterproductive, as it discouraged volunteers from going to the front lines. While Ebola captured headlines, other equator zoonotic diseases are also on the rise. Emerging viral threats, zoonosis. Diseases like monkeypox and hantavirus show how our interaction with animals dictates our health, whether it's the import of exotic bits or human moving into previously wild territories. We are constantly exposing ourselves to new pathogen in the zoonotic pool. Sometimes these pathogens do not need a direct bite. They use a middleman. West Nile virus arrived in New York, the NYC, in 1999 via an infected bird or mosquito on a plane. It uses birds as reservoir and mosquitoes as the vector. It is now permanently endemic in the United States, causing thousands of cases of encephalitis every year. Similarly, the Zika virus recently demonstrated how mosquito-borne illness can have devastating effect on the next generation. Zika, the devastating vector. Zika caused a global alarm not because of its effect on adults, which is usually mild, but because of its link to microcephaly in newborns. This outbreak highlighted the intersection of public health, reproductive rights, and socio-economic barriers in places like Brazil. Why are we seeing so many of these new diseases now? The answer lies in the environment. So, environmental factors of emergence. Human activity is driving disease emergence. Ecological change, deforestation brings us into contact with new species. Modern agriculture crowds livestock in ways that act as viral incubator, and global mobility ensures that no infection stays local or long. Now, where is this global speed more dangerous than with the virus we face every single year? The flu, influenza, and SARS. Influenza and SARS represent the most significant threats for a worldwide respiratory pandemic. To understand the future of the flu, we must look at its deadliest year. Historical impact. The 1918 flu. The 1918 pandemic killed more people than World War One. It was unique because it killed young, healthy adults by overstimulating their immune systems. Because the flu is RNA virus, it undergoes antigenic drift, changing its appearance constantly. This constant change requires a massive global surveillance effort. The annual surveillance and vaccines. Every year, the World Health Organization, the WHO, monitor global viral samples to predict which strains will dominate. This is a race against time, as a vaccine production takes more than 6 months. We also have monitor the ethics of gain of function research, where scientists create more dangerous version of the virus to study how to stop them. The greatest fear is a perfect storm, mutation in the avian flu. So avian flu H5N1 has 50% mortality rate in a human. Currently, it doesn't spread easily between people. However, if avian strain and human strain recombine inside a mixing pool, host like a pig, we could see a virus with the lethality of H5N1 and the transmissibility of the seasonal flu. While viruses are changing their customs, while viruses are changing their costumes, bacteria are building armor. The new bacterial threats. We are now seeing the return of bacterial threats that were once considered minor alongside entirely new variant. Let's start with an example of how ecological changes created a new disease. Lyme disease. Lyme disease is not new, but its prevalence is. By reforestation of the suburban areas and the elimination of predators, we have created an explosion of deer and mice. This is this in turn has led to a surge in the deer ticks that carry the Lyme spirochetes. Other bacteria are not just becoming more common, they are becoming more aggressive. The return of virulent Streptococcus. Group Streptococcus has resurged in flesh-eating form. This bacteria produced toxin that causes rapid tissue death and toxic shock. It is a reminder that even common bacteria can acquire new genetic weapons through horizontal gene transfer. A similar genetic upgrade happened to a common resident of our gut. Most E. coli is harmless, but the O157H7 strain acquired a gene for the Shiga toxins. This allows it to cause severe kidney failure. It spread through our industrial food system, from grounded beef to alfalfa sprout, showing how centralized food production can amplify a local contamination. The common thread in our struggle against bacteria is the fading power of our medicine. Biology of antibiotic resistance. Resistance is evolution in real time. When we use antibiotics, we kill the weak bacteria and leave the mutants behind to multiply. These bacteria can then pass their resistance genes to the other species via plasmids, effectively teaching other bacteria how to survive our drugs. This evolution is being accelerated by human behavior. The drivers of antibiotic resistance. Three things drive resistance. Number one, using antibiotic of viral infection where they do not work. Number two, patients failing to finish their prescription. Number three, most significantly, the use of antibiotic in livestock feed. In fact, 70% of all antibiotics in the United States are given to healthy animals to promote growth. No disease illustrates the danger of resistance better than tuberculosis. Tuberculosis. We will now look at tuberculosis or TB, a re-emerging disease, and prions, which represent an entirely new category of pathogens. Why did TB or tuberculosis come back after we thought it was gone? The tuberculosis, the resurgence of a killer. In the 1980s, TB or tuberculosis surged alongside the HIV epidemic because HIV weakens the immune system. It allows latent TB to become active. Combined with homelessness and urban crowding, TB found a perfect environment to spread once again. To fight TB, we must understand the difference between being infected and being sick. Tuberculosis latent versus active. One third of the world is infected with latent TB, but only 10% will ever develop the active contiguous disease. However, for someone with HIV, that risk jumps to 50%. The synergy between the two diseases makes them a syndemic, two epidemics that fuel one another. Treating tuberculosis is difficult because the regimen takes 6 months, leading to the rise of resistant strains. MDR or multi-drug resistance TB and DOTS approach, DOT directly observed therapy. When patients stopped taking tuberculosis medication early, they developed multi-drug resistant tuberculosis. To solve this, public health uses DOT, directly observed therapy. We literally watch the patient swallow the pill. This unconventional social intervention is often more effective than the medicine alone. But even DOT is not enough for the newest strains. XDR tuberculosis is resistant to almost everything we have. It has mortality rate similar to the pre-antibiotic era, while we have seen some breakthroughs in new drug cocktails. XDR-TB remains global security threats that requires strict international monitoring. Prions protein-only pathogens. Prions are revolutionary because they contain no DNA or RNA. They are simply misfolded protein that convince other protein to misfold. This leads to brain wasting disease like mad cow and CGD. They are incredibly difficult to destroy, surviving standard sterilization and cooking. This brings us to our final topic: how we protect ourselves from these threats, whether natural or intentional. Public health, global surveillance, and bioterrorism. Our final section covers the role of public health in defending against the unpredictable, including the threat of Bioterrorism. How does a disease outbreak differ from the traditional attack? The biological attack won't look like an explosion. It will look like a busy day at the hospital. In 2001, anthrax attacks proved that our first responders are not just police and firemen, but doctors, nurses, and lab technicians. Our best defense against bioterrorism is a strong, well funded public health system. Let's wrap up by looking at the path forward. The conclusion: strengthening the system. We cannot stop microbes from evolving, but we can change how we respond. This requires a global surveillance, smarter antibiotic policies, and a return to the basic of sanitation and immunization. The struggle between human ingenuity and microbial evolution is a permanent. This is the end of this chapter. See you in the next chapter, and goodbye. Thank you.